Okay, so I guess most people are here. So yeah, my name is Jason Jones. I'm a professor here, College of Optical Sciences, and I'll give you a little bit of a tour of our lab, a virtual tour today. I have one of my students, Kane, is going to take over here in just 2 minutes, and he'll show you the actual lab and one of the experiments that we're working on. So we have a number of different experiments in a couple of different labs, and they all involve sort of developing novel laser systems for different experiments. And so we're going to give you an example of one of those experiments and the type of laser that we use in that. And so feel free to stop me anytime with questions. Just going to show you one slide here, if that works. So the lab we're going to show you, we do some experiments in laser spectroscopy of plasmas. And so this shows a vacuum chamber, and a little cartoon shows where a laser pulse comes down and it ablates a metal sample and it generates a plasma. And one reason for doing that is if we want to determine what that piece of material, that solid material, is made out of, using laser light, it's difficult to do it when it's an opaque solid piece of material. So we first ablate it with a high energy pulse and create a plasma. And then after a microsecond or so, the plasma starts to cool and it forms atoms, and there's some ions and eventually molecules. And then we can probe that plasma with a second laser beam to try and determine optically what the elements are by looking at the discrete absorption lines. Now, this is a common technique if you use a spectrometer to look at the emission of the plasma. And the best example I can give is the Mars rover that's up, and other similar things up on Mars right now, where they take a laser and they'll ablate a rock or some material, and they'll look at the light emitted from that sample on a spectrometer and try and determine the composition of different materials. We're developing unique laser systems and techniques to overcome some real fundamental barriers for this in different applications. And one example that got us started actually is in nuclear forensics. If you have some material, radiological material, and you want to know if there's an unnatural enrichment of one isotope over another, you need a much higher resolution than typically you can get with the other techniques. So we've developed a novel laser system to probe the laser-induced plasma to give us more information. And I'll just leave it at that. So I'll let Kane take over and show you the lab and give you a little bit more background on the laser that we use, that we've developed for this, and just show you some of the experiments and some of the information we get from that. Does anybody want to pause with any questions before I turn it over to Kane? Okay. Go ahead, Kane.
All right. Okay, I thought you have some frequency comb slides to show. Okay, I will take over from here. All right. So I'm Kane. I'm fourth year PhD student in Jones Group. So before I start, let's look at time. I'm going to talk about a little bit the technical part. Then we have a lab tour. So in the end, I can show you some data of this experiment. So before we start, so generally here, so can you hear me okay, Jason?
Yeah, it's better the closer you are to your computer.
All right. So here, generally, this is a precision measurement spectroscopy group. So we are doing femtosecond lasers. So femto means 1 times 10 to the minus 15 seconds. Yeah. So specifically, our laser is called frequency cone. It's one kind of ultrafast laser. The reason people call it frequency cone is because the spectrum of it is cone-like. Yeah. So if you look here, I don't know if you can see it. So if you look at the spectrum of this laser, it has a lot of spikes. So this cone teeth structure make it called frequency comb. If you are interested in this technology, you are welcome to look, just Google 2005 Nobel Prize is awarded to this technique. Yeah. So here we have the femtosecond lasers, and specifically we have two lasers. So with two frequency combs, we can apply a dual frequency comb spectroscopy. So it's very similar to the Fourier transform spectroscopy, where you have a Mach Zehnder interferometer. So here is your yeah. So this is one of the interferometer. You have two arms. Then you can translate one arm and let's say you have some known sample in one of the paths. Then using this technique, and when they interfere, you measure the signal at your detector. So in the end, you just do a Fourier transformation that will give you the spectrum of your signal. If you are curious why this is true, that's because the Fourier transformation of autocorrelation gives you the spectrum of power density. Yeah, so there is a mathematical theorem behind this. Yeah, I hope I don't confuse you too much. And feel free to interrupt me when you have questions. Yeah, so here, what we are doing is basically the same. So we have our lasers. Actually, we have two lasers. So we look at the interference of our laser. So one laser goes through the sample and beat with the second laser to generate signal. Yeah, I think maybe you are bored. So let me show you the lab. All right. So here, yeah, so this is a ultrafast lab. So if you see this box, this is one frequency comb, one femtosecond fiber laser. So we use ytterbium fiber laser. The wavelength is around 1 micron, 1060 nanometer. And here we have a second one. Yeah. Then it's 1 micron, but you see some green light here. That's because we are doing a second harmonic generation. So if you look over there, there are two crystals. That's the BBO crystal that upconvert the light frequency from 1 micron to 532 nanometer. Yeah, so the photon picture will be two photons combined into one photon. So the energy is doubled. Because the infrared 1 micron is invisible, but after it converted to green, we are able to see it along the optical table. Yeah, so this is the chamber Jason just showed. You see here. So we use this powerful ND-YAG laser. So you see the light comes from here, then hitting this mirror, then focus down onto a sample inside this chamber to generate laser-induced plasmas. Then those lasers, you see the green light here goes through this sample, then it's hitting this, it's hitting this mirror here, then combined with another light. I will show a schematic just in a couple of minutes, but then let me walk you around this lab. So a lot of part of this lab is to stabilize our laser. You see, we use thermal pad to isolate the thermal and acoustic effects of this room. Okay, so here the laser comes out, then it goes through this amplifier to get more power. Then you see here, that's the grating pair, which can compress the pulse. I mean, it offers negative group delay, GDD, group delay dispersion, to compress the pulse to a shorter, like 100 femtosecond. And here, yeah, so if you're familiar with this year or last year's Nobel Prize, that's the CPA system. That's the chip pulse amplifier. So we send in a lamp pulse into this amplifier, then it has more energy. Later on, we compress it, then do the second harmonic generation for the spectroscopy. And here, I want to show you some electronics of this lab. You see here, these are the servos to stabilize those two lasers. So generally, those two frequency combs, we use two CW lasers. Here is one rock laser, one N-Pro laser. We use two CW lasers to stabilize two ultrafast lasers. And we use another cavity, reference cavity, to stabilize those two CW lasers. So it's like two stage. The ultrafast laser locked onto CW lasers. CW laser is locked to this ultra stable cavity. So this is like a mini LIGO. So what LIGO use to lock their kilometer arm is one technique called Pond Driver Hall locking. So here we are using the same type locking, but it's much shorter. I mean, it's only, that cavity is inside this box is only 10 centimeter. So, and these servos are used to generate, I mean, error signal, then lock these lasers one to the other. Yep. Hope you, yeah. If
Kane,
you have,
I have a question for you. What in your frequency comb boxes, what kind of lasers are those?
Great. So inside this laser box, that's the ytterbium fiber laser. We use the polarization rotation method to mode lock it. So it's mode lock laser. So if you look at here, that's the spectrum of this laser. You see that range from 1060 to 1090, centered at 1060. Yep. Did that answer your question?
Yes.
Great. Then let me see how many time do I have. Okay, let me show you some data in the end.
Okay,
Oh, I have one other.
Kane,
Yep.
I have a question to maybe clarify. So the light from the laser is around 1 micron, you can't see it. And then we double the frequency of the light so that it is now green. And then with that green light, can you tell them what atoms are we trying to detect in the sample by using the green light?
Yeah, so we're just ablating stainless steel, so iron. So iron has 3 transitions around 532 nanometer. That's the reason we double our light from 1 micron to green 532. Then we can see the absorption of those 3 transitions of our light. Yep.
I have a question for you.
Yep.
Kane and Jason. I've never seen your lab, but this is for Kane. How hard is it to keep this thing aligned?
Aligned? Good question. You know, after working for 2 or 3 years, I need just several days to align this part. But in the very beginning, it may, I mean, if you know how to do it, it's very quick. But the point is, like, in the beginning, I need to learn how to do this. That may take like half a semester, 1 semester, or yeah. Then later on, to build this part, I only take like 2 or 3 days. But the design part takes longer because usually we have a plan, then we need to do calculation like how far we, for example, here, you see this part, that's a delay arm. So in order to make the physical length right, we have to calculate, like this maybe is 10 centimeter, we want 40 microsecond separation, then how long should here be? I mean, you maybe ask if it's only several centimeter or even 1 meter, light, the speed of light is 3 times 10 to the 8 meter per second. That's only nanosecond separation. You are very right, because this technique can down convert the time, like it will convert nanosecond to microsecond due to the sampling of this technique. Yeah, so I skipped some details, but yeah, so not only the alignment, but also the design. I mean, for real research, it brought a general picture is like we have a goal, then we design it. I mean, if we spend more efforts when we design the optical path and consider some like consider everything in the plan, it's easier to build it. Yeah.
And back to Jason's question, why might you be looking at iron?
Why are we looking at iron? Oh, is the audio still there?
Yeah, we can hear you. Yeah.
Okay. Yeah, Kane, did you want to answer that? Or iron is just something that's easy to start with. We've looked at things like iron, rubidium, neodymium, atoms that are strong absorbers and that have properties that will mimic maybe the things that are of more interest for some of these experiments. So for example, we don't want to use uranium in our lab. It's a lot more complicated and we don't need to, but one application is looking at whether or not there's uranium in a sample, and if so, what's the isotopic ratio of its two major constituents. So we use surrogates of different atoms that have similar properties.
Yep. Besides iron, we also look at other elements. I mean, given the spectrum we have, we are free to look at all the elements that has absorption at this spectrum range. So iron is easier to start with because stainless steel is easy to get and ablate.
So do you want to show them, Kane, what it looks like, the data you get when we do the ablation, and we can, as a function of time, see the absorption and signature of anything in the laser plasma?
Yep, let me share the screen. So let me open my PowerPoint. Okay, here. Yeah. Can you see my screen, Jason?
Yeah, I think that's good.
Great. Yeah. So here we're doing the dual frequency cone spectroscopy. It's one specific technique for spectroscopy. And here is the schematic of the lasers I just showed. So if you see here, let's see a laser point. Yeah. So here we have two frequency cones. So one cone, let's say this one, it goes through this ion plasma. So this is the chamber. We use this Nd:YAG laser to ablate it to create the ion plume or ion plasma. So if it's a solid, it's hard to do absorption. So this technique can ablate it into a gas form such that the light can go through it. Then once it goes through this plasma, some of the light is absorbed. So here, this beam splitter combines two cones. So it's like this cone bead with this local oscillator, then it hits a grating. So grating will just separate all the colors. And we just use a slit to physically select which portion we want. Then we use detector to detect the signal. And I skip the electronic part to control the delay. And here, you see, here is the energy levels of those three transitions we are looking at. So these three transitions, they are all around 532 nanometer. You see here is 532.8, 0.85, 0.4. So they are little separated. And you see here, the ground state is lower, which means if the plasma is not too hot, the population of those electrons obeys Boltzmann distribution. So most of them occupy the lower energy levels. So which means a transition with a lower state has stronger absorption because more atoms, more electrons occupied here. So here is the data we measure. You see, for each delay, so the delay is the time after laser ablation. So once we ablate it, the plasma is formed, then gradually cooled. You can see, I mean, roughly you can see that from early time to later time, the plasma absorption increase, then decrease. So if we just see a cartoon, you will see the middle line, which corresponds to this line with the lowest energy level. It increase, then decrease, because as plasma cools, the population decrease from higher state gradually to the lower state, which means the population here increase first, then decrease. That's the reason we see the middle line increase, then decrease. So from this measurement, we can calculate the area under these curves. So I think you have heard about Beer's law, right? So Beer's law tells us that the area under absorbance is proportional to the alpha times L, which is the absorption coefficient times interaction length. And if we combine that with Boltzmann distribution, we are able to know the temperature and total number density of that plasma. If you look at here, from that measurement, we can know the plasma temperature decreased from 7,000 Kelvin to about 4,000 Kelvin after 100 microseconds. And the total number density, I mean, times L, we can also get that quantity out. So this quantity is not easy to get with other spectroscopy technique, because if you do the emission spectroscopy, the light emits all the way. But for absorption spectroscopy, it's easier to get this quantity. Yep, that's the rough overview. Jason?
Okay, thanks, Kane.
Yep.
Yeah.
Thank you both, Kane and Jason.
Yep.
All right. Well, yeah, that was a lot of details there, but it gives a good example of the unique laser systems he's building in order to try and do the spectroscopy of laser-induced plasmas. Yeah.
Yeah, that was pretty cool.
Yep.
Any other questions from anyone? I saw Luke put one in. If not, thank you very much, and we'll return to our regularly scheduled room.
Okay. Thanks,
Thank you
guys.
very much.
Thanks. Take care.